If you look across the globe and back through time, every culture has looked up at the night sky and wondered, are we alone? And with the possible detection of signs of life on a planet far beyond our solar system, we are getting tantalisingly close to finding an answer. As a space scientist, I explore the universe, and I'm more and more convinced that there is life out there. So in this series of lectures, we are going to look and ask the question, is there life beyond the Earth?
Leaving Earth orbit. Take third exit to Mars. Mars rover collected. Boarding. James Webb Telescope. Acquired. Navigate off-road. Voyager probe acquired. Approaching light speed.
Welcome to the 200th anniversary of the Christmas lectures from right here in the Royal Institution, supported by CGI. Now, let's go back 4.5 billion years to the time soon after the birth of the solar system. That was quite a tumultuous time. Things were moving around all over the place, and sometimes there were real cataclysmic crashes. What we just saw there was the formation of the moon. I'm Dame Dr Maggie Aderin-Pocock, and I describe myself as a self-certified lunatic because I am just mesmerised by the moon. So in that early solar system, we think their body about the size of planet Mars crashed into the early Earth and sent dust and debris up into the atmosphere. That coalesced to form our moon. Now, this is the Earth as we know it now, but back then the Earth was like a molten rock, and the moon was also a molten rock, but in orbit about it. But I would always like to travel back to that time because the moon was much closer to planet Earth, and it must have been like a golden orb in the sky, quite magnificent. So all my life, I have been absolutely fascinated by space. And I think the first trigger for me was actually my father. So this is a picture of my father. Unfortunately, he's passed away. But he actually got that spark of interest in space. Because he used to tell me tales about when he was a child, because he was born in Nigeria. And living in Nigeria, he used to actually have to travel 12 miles to get from home to school. And that journey was on unlit roads. And so when the moon was up, it would light his way, and so the moon was my father's friend. So if it was my father's friend, it was going to be my friend too. Now, in inner city London, there is lots of light pollution. So when you look up at the night sky, you don't see many stars. But what you can see is the moon. As a child, I used to always love looking at the moon. So when I was about 6 or 7, I dreamed of getting into space. Now, I co-host a television show called The Sky at Night. And it's the longest running science show in the world. But my predecessor was a chap called Patrick Moore. And he'd say, if you have a telescope, this is what you can see in the night sky. And so I decided then that I would build my own telescope. And so this is when I was about your age, I was about 14. But to show you how I did that, I'm going to need 2 volunteers. Oh, I love the way the hands go shooting up, okay? Perfect, okay. Both of you, yes, with your matching Christmas jumpers, please come on down. First of all, let's start off. What are your names? What's your name?
Sophie.
Sophie. Very nice to meet you. And what's your name?
Emma.
Emma. Sophie and Emma, thank you. So you're going to be part of this demonstration. Now, Sophie, what I want you to do is I want to show you how I made my own telescope. And Emma, if you can come over here, we'll be doing a demonstration on that in a few minutes. Thank you. Okay. Now, first of all, I've got a powder in here. So what this is like an abrasive powder. And what I'm going to do is I'm going to sprinkle that abrasive powder on this piece of glass. So this is just a plain piece of glass. And then what I'm going to do is I'm going to add some water. And I'm going to smush that around. But what I'm doing is making an abrasive paste. And I'm going to put this piece of glass on top of that piece of glass. And then what I did, I spent many, many months sort of grinding. Now, OK, you give it a go. OK. So what you're doing is you're actually grinding that piece of glass to shape it. Now, I'm going to leave you doing that. In the meantime, what I want to do is talk about the history of the telescope. Now, the first person to apply for a patent for the telescope was a chap called Hans Lippershey. Now, he was a Dutch spectacle maker. So this is about sort of in 1608. And spectacles were all the rage, and they'd just been sort of invented. And so now, if you step over here, what he realised is if you put a lens which you use for reading and a lens that you use for distance viewing together, and you move them around, what you get is magnification. Now, Emma, I don't know if you can see at the back of the room, yes, someone is holding a sign there. Now, I can see my favourite planet is... Now, can you read the bottom word?
I think it starts with an M, but I'm not sure about the rest.
OK, so it's a bit blurry, OK.
Yeah.
Now, what I want to do is do exactly what Hans Lippershey did. Sort of move these lenses around and see if we can actually see that image up there. So if you can you look through? OK, perfect. Can you read it through here?
Mars.
Ah, OK. But that's what Hans Lippershey did. He effectively put these two lenses together and got magnification. So thank you. A round of applause for our volunteer. Thank you. So, that is what Galileo did. He took a telescope like that, oh, lovely, and made it into something like this. So this is effectively a Galilean telescope. And so you've got a lens at one end, a lens at the other, and then you can actually sort of adjust the focus, just as we were doing there, with this bit here. Don't forget, we're going back to 1608. And if you've ever seen any old buildings and the glass or in the windows of those old buildings, it's not very good quality glass. And so the question was, could you still get magnification, but without passing the light through the lens? Well, that brings us back to this demonstration. Now, do you want to give it another grind again? Ooh. So with that abrasive paste, can you feel what's happening?
Yes.
Yeah, because I think you're actually sort of grinding away the glass.
Yeah.
And what actually happens is, the one on the bottom becomes convex, and so it's like a hill, and the one above becomes concave, so it's like you scrape out the glass. Yeah. And now, see, when you are grinding, that results in a shape that is a spherical surface. Now, the problem with a sphere is it doesn't bring light to a nice tight focus. Because what we're trying to do is have a mirror that takes light from a very, very distant object. It hits the glass mirror, and then we bring it down to a focus. Now, unfortunately, a spherical surface can't do that. But what we can do is continue working the telescope mirror to form something called a parabola, which is a different shape, but it brings light from a distance to a sharp focus. And so that's just what we did. So thank you very much. I think a round of applause for our volunteer again. Thank you. Perfect. So what we actually need is to coat that glass with something like aluminium or silver to get a really shiny surface. And that's what we've got in here. So this is the basis of a new telescope. Now, the person who came up with the idea of this telescope was Sir Isaac Newton. And Sir Isaac Newton realised that you could actually get magnification by using a mirror. But the light path through this is very different. And I can show you with smoke and lasers. So thank you. You should put the lasers on. Ah, see, smoke and mirrors. That's what it's all about. Ooh. Now, at the moment, these lasers are representing the light from a distant object, so maybe a star or a galaxy that is a long, long, long way away. So the light comes in nice parallel lines. And then what happens is that light will travel through the telescope and it will hit our reflecting mirror. And then that mirror, as we said, is designed to actually bring that light to a nice tight focus. So it throws the light back up towards this flat mirror here. Now, this flat mirror you can buy off the shelf. And what that does is if I take the cap off and a bit more smoke, you might be able to see the laser light coming out through the top. Can you see the laser light coming out of the top? So that light has travelled from a distant star, travelled through the telescope, reflected off our primary mirror, it goes up to this secondary mirror, and then it is sent out to our eye. Now, These days, we have very good quality glass. But the challenge is, if you actually want to make a really big telescope, imagine sort of getting a lens that big and grinding and polishing. It's really quite hard. And so now, for the bigger telescopes that we use right here on the ground, we actually use the Newtonian method. And what I was making was a Newtonian telescope, because it's quite a simple design. And so now we have some amazing telescopes out there. Telescopes like the VLT. Now, VLT stands for a Very Large Telescope. That is truly the name of this telescope, the VLT. So you saw the mirror at the back end of this telescope. The primary mirror of these telescopes is 8 meters in diameter. It's not just one very large telescope, it's 4 very large telescopes, each one with a primary mirror of 8 meters. But the VLT is getting quite old. It's been out there for 25 years. And so now they're building the next generation of space telescope. And we simply call that the ELT, the Extremely Large Telescope. And this is it. The ELT actually has a primary mirror 39 meters in diameter. And so now this isn't a single block of glass. It's made actually of a number of sections which are put together to make this glorious telescope. So the ELT will probably be coming online in about next sort of 2 or 3 years. We'll point it up at the night sky and get glorious images. But the telescope I hope to see in my lifetime we simply call the OWL. And that stands for the Overwhelmingly Large Telescope. Truly, I'm not making this up. And so this is a picture of the Overwhelmingly Large Telescope. If we build this telescope will have a primary mirror of 100 meters in diameter. So we're talking about a mirror the size of a football pitch. And of course, with a telescope, the bigger your mirror, the more light you can gather, and so the fainter objects you can see. Now, I mentioned that I ground and polished my own telescope mirror when I was about 14 years of age. And when I actually got the whole telescope together, I was so excited. And I kept on thinking, so what do I want to have a look at? What is my first object in the night sky that I want to look at? And so, of course, the first thing was the moon. Now, it turns out I was following in some very good footsteps, because one of the first things that Galileo did is he also looked at the moon. And these are the images he took. This is Galileo sort of looking through the telescope and making a drawing of what he saw. You see all sorts of craters and all sorts of things on the moon's surface. Before that, people thought the moon's surface was just a round sphere, but now there was details on it, details you could see with a telescope. And so some people started speculating, perhaps some of those darker patches are sort of large oceans on the moon's surface. And if you have oceans and mountains and things like that, maybe there is life on the moon. And so what I'd like to do is invite someone who actually works here at the Royal Institution, Charlotte New. So, Charlotte, you work here at the Royal Institution, and I think you've got something from the archive here to show us.
I have, yes.
Okay.
So first we have this wonderfully old book that was first published in 1638. 1638, and it was published by and written by a guy called John Wilkins, who was a clergyman and a scientist.
Ah, yes.
And it details information about the moon, so it has a very interesting title piece.
Okay, lovely. And so this is a discourse tending to prove that 'tis probable there may be another habitable world in the moon.
In the moon.
Oh, yeah. So I think inspired by things like Galileo's pictures and pictures that people were taking with telescopes, from seeing that surface and realising that it's not smooth, people started to speculate as to whether there's life on the moon.
Indeed.
But I think they went further as well, didn't they?
They did, and he even goes on to say on another page here that you can get there by means of a flying chariot.
So they were talking about taking a flying chariot to the moon and hopefully, I guess, to meet the moon people.
Indeed.
Perfect. And so that was the current state of technology. We started using the telescope, we were looking at the moon and thinking that there might be life out there. So the next important breakthrough was, I guess, photography.
Photography, yes.
And we've got an example here.
Yes, so this is a wonderful glass plate taken by Warren de la Rue in 1859, and it's one of the first full pictures of the moon.
Okay, and so we've moved on sort of some 200 years now.
Yep.
So photography was quite new at this stage.
Yes, so it's actually announced here in 1839.
Oh, right, yes.
Part of our history.
Part of the history, lovely. But I think this is a glorious image. I see, looking at up there, I would like to have a projection like that in my room. As a self-certified lunatic, that would be lovely to have.
Indeed, indeed.
So thank you so much, Charlotte. It was lovely to see these exhibits.
Thank you very much.
Thank you. So that's what I find most interesting. It's the advent of photography in terms of astronomy was a major leap forward. And for many, many years, we were using photographic plates to capture images of the night sky, but in glorious detail. Then we started taking photographs of what we saw through a telescope. But then the next step forward was actually to get out there. What if we could get closer to the moon, not through a telescope, but actually getting physically closer to the moon? And one of the first probes to do this was actually called Luna 3. Now, Luna 3 was made by the Soviet Union, the USSR, and it actually went on a journey out there into space and went and orbited the moon and came back home. Now, one of the things you might not have realised is we only see one side of the moon. That's because as the moon orbits the Earth, the moon spins on its axis, but as it orbits, the same side of the moon is always pointing towards Earth. And so people got quite excited. Maybe that's where the moon people lived, on the far side of the moon, which we couldn't see from Earth. Now, we don't have any pictures taken by Luna 3, because that was quite some time ago, but I'd like to show you this picture. Now, this picture is actually a real picture, and it shows us the far side of the moon. So there is a probe with a camera on it, and it's looking towards the moon and towards the Earth. First thing to say about this image is the moon people are not there. But I think this picture is quite amazing, because it shows you the moon, and it shows our planet Earth. And so it just sets the scale. As I say, this isn't Photoshop, this is a real image. So, again, we've gone through that journey. We look at the moon with the naked eye. We look at the moon with a telescope. We take photographic plates. We actually journey out to the moon and then come back. But the next step, of course, was landing on the moon. And that happened in 1969. And yeah, with Neil Armstrong stepping out onto the moon's surface. Now, the moon landings were very much driven by a race. It was what they call the space race. So it was the USSR against the USA. And they were both trying to show, that they were the better nation or they were the better people. And so they would have this technological battle in space. But since then, we've been working in an era of collaboration where different nations actually pool their resources in space. Space is incredibly expensive. And so in 1975, you get things like the formation of the European Space Agency. So the countries of Europe putting their money together to go further into space. Now, I am incredibly excited because in the theatre today, we are going to be joined by the latest generation of ESA astronauts. And they're going to come into the theatre here, and this is Rosemary Coogan, Megan Christian, and John McFall. Please come in. I can't help it. I always smile when I see astronauts. So thank you very much for joining me today. No. Now, Rosemary, I'd like to start with you. Now, we were talking about international collaboration, like the formation of the European Space Agency. Why is that important, and what does it mean to you?
Yeah, it's so important. I absolutely love working with people from all over the world, all over the planet. It really started for me when I was in my 20s, the first time I lived abroad, and it was completely life-changing. Because for space, it is so important. To get to space, to live there, is incredibly difficult. It's something we can't do alone. And so we need the countries to work together. We achieve so much more when we do that.
Yes.
And it also gives us platform for countries to work together towards a shared goal at times where I think we really need it.
Yes. And that's what I really like. From space, you don't see countries, you don't see barriers. You just see planet Earth. And I think it's really lovely that space can unite like that.
Yeah.
Perfect, thank you. Now, Megan, why is it still important to send humans into space? And especially when we're looking for sort of signs of life out there?
Well, we are doing a really good job with robots on Mars, right? We have rovers. But rovers can only go so far and so fast. So we really need humans there as well, because humans can do things faster. Humans have a kind of intuition and are really good at problem solving. So if we want to speed up our search for life elsewhere, we need to send humans there to do it.
I'll happen to be that human.
So are we.
It's slightly more likely for you, I think. Yes. Now, John, I'd like to ask, what does it take to be an astronaut?
Well, typically astronauts come from a test pilot background or a science background, usually. Now, all of us actually here come from a science background. Me, in particular, I'm a doctor, medical doctor and orthopaedic surgeon. But what's interesting about astronauts is we are not brilliant at any one thing. And that's the thing about being an astronaut is you actually have to be good at many, many different things. So not just have a scientific background or a test pilot background, but be good communicators, be resilient, problem solvers, self-aware, all sorts of stuff. So you need a broad set of skills.
Lovely. Now, John, I believe you're the first person with a physical disability to actually be certified for life on the International Space Station.
Absolutely, yes. I'm a leg amputee. I lost my leg on a motorcycle about 25 years ago, and I use a prosthesis. And a couple of years ago, the Space Agency, European Space Agency, wanted to see if it was possible to clear the path to space for an astronaut with a physical disability. And at the beginning of this year, actually, I was the first person with a physical disability, as you say, to be medically certified to fly to the International Space Station. This is a world first.
Yes, I know. But I think I find it really exciting because it is opening up sort of that life in space to more and more people. So thank you very much. Now, John, if you could stay with me, and Rosemary and McGann, if you could take a seat on the hot step, I think you'll be joining me again later. I think big applause, what the heck. Thank you so much. Now, John, we were talking about earlier what it takes to be an astronaut. And so I effectively want to put you through your paces.
Oh, dear.
Yes. But on top of that, I want to give you a bit of competition.
Oh,
okay, so now I need a volunteer for the audience, but I need someone who is good on fairground lives, who doesn't mind getting, spun around and things like that, okay? Oh, okay, that is a classic Christmas jumper. Come on down. Lovely to meet you. Now, first of all, what's your name?
I'm George.
George. Now, if you'd like to come up here, this is your challenge. And so what we have here is a dexterity test. So I'm going to hold up one of these. Each one of these pegs has a planet on the outside. The name is also written here, and that needs to match a planet on this board with holes. And so what we're going to do is I'm going to get you to put these in. Now, they're quite a tight fit, OK? And so now, John, I think you've done something like this before.
We do some reaction stuff and sort of perceptual speed, this sort of stuff in the selection, yeah.
So you're on home turf here?
Yeah, maybe a little bit.
Maybe, OK. But to make it a little bit more interesting, what I want to do is, well, let's just do it. Bring on the chairs of doom. Yeah, unfortunately, I think due to budget cuts, the chairs of doom actually got a bit cut down, but please take a seat. So what we're going to do here, we're going to spin you around for 20 seconds, so you'll be a bit disoriented, then I want you to get up and go and put the pegs in as quickly as you can, and we're going to give you 15 seconds to do that. OK, yes. And now, John, if George wins, he's the new astronaut.
Yeah, you're leading with this on, yeah.
OK, start the clock. OK, so 19, 18. OK, we're spinning quite fast, actually. I'm glad I'm not doing this. I don't think I'd survive. Oh, John, you're going into orbit. Come back.
Am I going to still be in the theatre by the end of this?
I know. So how are we doing? Oh, 6, 5, 4, 3, 2, 1. OK. OK, so now we're trying to... I will be marking your accuracy as well. So we've got to count down. So 9, 8, 7, 6, 5, 4, 3, 2, 1. Put your pegs down. Oh. John. That was sneaky.
Right to the line.
Right to the line. Make the most of every second, OK? Ooh, I don't know what happened to Jupiter there. But, OK, so how did you find that? George, let's start with you.
It was quite difficult because I was still spinning.
Reeling, yes, from the chair. And so let's see. OK, you've got 1, 2, 3, 4. I think that's a good effort. OK, but now over to the trained astronaut. OK, how many have we got? 1, 2, 3, 4, 5, 6. OK. So, I'm sorry, you don't get the suit. Well, thank you so much. And a big round of applause for George, please. Hold on, mate. So thank you so much, John. And we've put you through your paces, and you've survived. So if you'd like to go and sit on the astronaut seat. And Rosemary, would you like to come up? Now, Rosemary, one of the things, you haven't been into space yet, but you're in training, and you're training for a mission to the ISS. Is that correct?
Yeah, that's right.
Lovely. Now, let's see what the ISS is. The ISS is the International Space Station.
Yes. So this is the International Space Station. It's kind of as it sounds. It is a station, a laboratory that is flying through space.
OK.
So it's flying above us, 250 miles above the surface of the Earth, and it's going 18,000 miles an hour. So it's going very, very quickly, and it goes round and round the Earth every 1.5 hours.
Ooh. So every 45 minutes you get a sunrise and a sunset?
Yeah, 16 times a day
16
on
times
orbit,
a day.
you'll see a sunrise and a sunset. If you're awake all day.
If you're awake all day. And so we've got the solar panels, we've got the sort of International Space Station, and also we've got these different modules.
Yeah, exactly. And, you know, we have modules at the front from NASA, from ESA, from JAXA.
Japanese Space Agency.
Yeah, that's
Yes.
right. And we have Roscosmos at the back here.
Russian.
So there's 5 different space agencies all contributing to this. We've got 23 countries already within ESA, so it's loads and loads of countries. It really is international. And essentially, it's a place to do science because we have microgravity or weightlessness when we're on the ISS. And we can learn so much in this environment that we can't learn on Earth. So the majority of these modules are laboratory scientific modules, but we do have a few that aren't. So right in the middle, we've got the cupola here, where we see these iconic views. And just above it is what we call Node 3. And this is where we have the gym, we have the toilets, and just next door to it is Node 1, where we do our food preparation.
OK, and speaking of food, I think we prepared a snack earlier.
So we brought in some space food just because I thought it was kind of interesting to see the different types of food that we can eat in space. So this here is a space chocolate bar. And it actually says on the back, the healthiest chocolate bar in the universe, which I thought was really fun. And you can just
That's quite a
unwrap this and eat this. And then we have lasagna, which just gets put straight in the oven. And this is macaroni cheese, which has been completely dehydrated.
Ooh.
So you use this opening here to put in hot water from the machines. And in 5 to 10 minutes, it will become beautiful macaroni cheese again.
When you say beautiful, have you tried any of this food?
I haven't tried the macaroni cheese, but I've had some other space foods, and I thought it was great. And, you know, sending it up like this, it's much, much lighter.
OK, lovely. But after sort of a number of processes in the body, I guess food has to come out. Now, going to the loo in space, I was told, was challenging. I think that's the best way to put it.
Yeah, and it's something we get asked about a lot, and it's something that I wouldn't have really thought about, you know, before being in this role. But actually, when you go to the toilet on Earth, everything kind of goes down, you know where you're going, and it's easy and simple. But in microgravity, you go to the toilet, things can start floating around, and you need a way to stop that happening. Yes. Exactly. So actually, they've got a great system. So to go for a wee in space, you have a funnel attached to a long hose that has an airflow going through it, and when you wee in there, you know exactly where you're aiming.
OK,
and
lovely.
Is
and it gets sucked away. Yes.
Exactly, it's sucked away and recycled.
Oh, recycled.
Into fresh drinking
so
water.
let's just think about that for a moment. So pee and other things go through the system and they get recycled.
Yeah.
Recycled into drinking water.
Yeah, all of the water on the ISS. So this is the sweat, the water we use to wash with, the water vapour and the air we breathe out, and our urine. It all goes and gets cleaned and turned back into drinking water. So it's amazing technology that we'll need as we go further and further afield.
OK, you're slightly putting me off the whole situation now.
Oh,
but
no, it's a great system. It works really well.
So fantastic. So that's food and going to the loo. But also, the International Space Station is getting a little old now. It's about 25 years old. And it's been a glorious collaboration, as you say, of countries sort of across the world. So what's coming next?
Yeah, so as you say, I mean, actually the ISS has had humans living on it permanently for more than 25 years now, which I think is really impressive.
Yes.
But in the next few years, it is going to be decommissioned. But there's still a lot to look forward to in terms of stations going around the Earth. We'll either have a new station or several stations, almost replacing the ISS. And beyond that, we actually have a collaboration between ESA and NASA going back to the moon, and these are the Artemis missions. So I know you've just been talking about the moon, so it's a hot topic.
Yes.
And we're really building upon what Apollo has taught us. It's more than 50 years since we've been to the moon. And this time, as we go back, we're going to be having Europeans go to the moon and around the moon for the first time. We're going to have a space station that goes around the moon instead of going around the Earth.
Ah, yes.
The first crewed mission of this of Artemis is actually our American and our Canadian colleagues are training for that next year already.
yes.
So it's happening really, really soon.
Now, I must admit, this is something which would be a dream come true for me. But we do actually have amongst us someone who has been to the moon. So I think he's with his handler, so no photography, please. But here he is. This is Shaun the sheep.
Thank you very much. Thank you. Yes.
So so this actual model of Shaun the Sheep has been into space, has been in orbit around the moon. Is that the case?
Yeah, exactly. This Shaun the Sheep actually did the first Artemis mission, Artemis 1, just a few years ago. He very bravely tested out all of the systems because there were no other astronauts on board to help him, and he has returned safely. And I had the pleasure of meeting him actually just after his mission for the first time a couple of years ago, and he's a great ambassador for it.
Yes. Well, he doesn't look frazzled by the whole journey. He looks pretty cool.
He looks really cheerful.
In fact, I'm sure he looked like that before he went, but yes. And so I have to say it does feel like one giant leap for lamb-kind. Okay, I'll go. So much for the career as a stand-up comic. And now, thank you so much for joining us, and I think a round of applause for Rosemary, please. Thank you. To find out more about plans of actually setting humans on the moon, I'd like to recall Megan to the stage, please. Thank you, Megan. Now, Megan, what are the plans for Artemis 2?
Artemis 2, there are going to be humans on board, and so they're going to be testing all the systems for an eventual moon landing from Artemis 3 onwards.
Okay.
So Artemis 2 is going back to a bit like Apollo 8. The first mission where we had humans going around the moon.
Now, it's quite interesting talking about a moon base, because as far as I'm concerned, we've been talking about moon bases for almost forever, since before we actually went to the moon. And so, but it is a very exciting prospect for me, but it has got its challenges. I think the temperature on the moon's surface, for instance, on the day side of the moon, where the sunlight is hitting it directly, I think it's about plus 150 degrees. But on the night side, where the sunlight isn't hitting it, it's about minus 150 degrees. And so we need to make sort of habitation and things like that on the moon's surface that can survive these extreme conditions.
And this time with the Artemis mission, we're going back to stay.
Now, I guess one of the challenges, if we're going to send resources to the moon, that's going to be expensive.
Yeah, that's right. I mean, think about it. You have to take everything with you to the moon. The moon doesn't have an atmosphere. You can't breathe. You can't go and stand on the surface of the moon and breathe what's there. So you have to take all that oxygen with you. You have to take all your water and all your food with you. And that gets really, really heavy. And it's already hard enough to get to the moon by yourself. So we want to be able to use the resources that are already available there. So we've found that there is actually ice inside the lunar dust, the regolith. And so perhaps we can use that. We can use the resources available on the moon to support us.
Okay, that sounds very exciting. And so now, to actually sort of demonstrate this in a little more detail, what I'd like to do is actually ask for a volunteer. Any volunteers in the audience? Okay, I've got a chap with a red jumper and a white shirt. Yes, you. Do you want to come on down? Oh, it's you. Thank you. Oh, pleasure. So first of all, what's your name?
Knuckle.
Knuckle. Very nice to meet you, Knuckle. Okay.
You too.
So what we're going to do is we're talking about utilising those lunar resources. Megan mentioned that on the moon we have discovered water. Now, what is the chemical makeup of water? Does anyone know? Actually, shout it out if you know. H2O. Good old H2O. And so that translates to hydrogen and oxygen. Now, Megan, you mentioned that sort of on the moon's surface it has no atmosphere, and so we need to take our own supply. Now, what we're taking from our atmosphere is oxygen, and that's what we need to breathe. So the fact that water contains oxygen is really useful. But then we're also talking about hydrogen. Now, hydrogen we can actually use to fuel rockets. And one of the nice ideas about having a moon base is we can use it as a staging place to go out to other parts of the solar system. The moon is smaller than planet Earth, it has less mass, so launching things from the moon's surface should be cheaper once you've got the base. And so what we're going to do is try and do a demonstration of that. So we have actually some water in this tube. So what's going on here is a process called electrolysis. We're passing a current through the water and it's splitting up into hydrogen and oxygen. And that's what you can see bubbling out of this tube. So what I want us to do is launch our own rocket. There is your rocket, and we're going to launch it into space. Now, I'm going to fill up the rocket with fuel, the oxygen and the hydrogen. Then I'm going to put it onto the launch pad. Then what we need you to do is actually launch the rocket. Now, you do that by pressing that red button, but it's a press and a hold. Because what I think many people realise here that hydrogen and oxygen are both flammable, so you will set out the spark, so you'll hold it down and you'll have a spark, and that will ignite the fuel inside the canister and whoosh, to the stars. So that's the plan. Now, I'm going to give you some ear defenders and also some glasses. So I'll put these on too. Perfect. Now, for health and safety, you're going to be the key operator.
Yes.
So what we're going to do is, first of all, I need to fuel our rocket. So this is the rocket. Now, it turns out that the hydrogen is lighter than air. So if I take this out, what I'm going to do is count for 10 seconds to fill up the rocket with fuel. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, put that back in there. Now I've got to get it on the launch pad quickly because I don't want that gas escaping. Yeah, that's a reassuring click. And then what I'm going to do is I'm going to step back, and then what we're going to do is a countdown from 5, and then you're going to press and hold, and we'll see what happens. Okay, so 5, 4, 3, 2, 1. Whoa! That's wonderful. So I'm just going to take this off. So thank you so much. That was a brilliant launch, very successful, and top congratulations, and a round of applause for our volunteer, please. Actually, thank you to all the astronauts. Thank you so much for joining us and sharing your experiences with us. So I think an extra big round of applause for our astronauts. Thank you. Now, it's quite interesting because I think many people might not be aware, but every time we do a Christmas lecture, one of the things we do is have a youth summit. Now, there was someone here in the audience that was actually at one of those youth summits. Now, Ella, I'm going to come up and see you, so excuse me. Now, Ella, first of all, can I ask you, how old are you?
So I am 17 years old.
17 years old,
yeah.
OK. So you were at the London Youth Summit, I believe. You were speaking at it?
I was speaking at the Youth Summit, yeah.
Lovely. And so what were you talking about?
So I was talking about the space economy. It started off with governments. Governments were running the space industry.
Yes.
And it wasn't until we had billionaires that there were people who could afford to ask that question of, how do we turn this into a business opportunity?
OK.
So we have Richard Branson, who has founded Virgin Galactic. They are looking at space tourism. Yes. So any of us could, in theory, be a space tourist. Yes. You also have a Jeff Bezos, CEO of Amazon and now founder of Blue Origin. One of Blue Origin's missions is taking all infrastructure and heavy industries up off of Earth and into space.
Wow.
And so effectively that would give us a greener future.
Yes.
On the flip side, you have Elon Musk, founder of SpaceX. He is looking at sending humanity to Mars. He really created a shift in this industry because he developed reusable rockets. That is what caused the shift, because now millionaires could access this industry. Ooh. And there are a lot more millionaires than there are billionaires. Yeah. This is a transition period. This is the new space age.
Fantastic.
Yeah.
Well, lovely to speak to you.
It was nice speaking to you, Maggie.
And I wish I was doing the sort of thing you're doing when I was 17.
Well, yeah, maybe.
Lovely to speak to you. And a round of applause. Thank you.
Thank you, thank you.
So we're exploring how we can utilise a moon base to actually travel further into the solar system. And it just makes so much sense. And so we're going to go on in our journey. But I think before we can understand a life on another planet, we need to get an understanding of life right here on Earth. And the thing is, we have a variety of life here. We have life up in the air. We have life on the land. We have life in the oceans. A variety of life. Now, what I'd like to do now is to invite some people in from the Natural History Museum, Shristi and Chris. Now, I'm quite excited by this, because I'm usually talking about things far away, the big universe. And now we've got a microscope, so that makes me very excited. Now, Shristi, you've been going around cemeteries and collecting samples. This makes me slightly worried. So what have you got in the jar?
So this is moss from Tower Hamlets Cemetery.
Okay, so this is just sort of normal moss?
Just regular moss that I did get them from gravestones, but,
We won't ask too many questions, I think.
It was very easy. You just kind of pick it up. Yeah, it's not hard.
Yes.
Yeah.
So, but why have you got this? Why is this of interest?
So we were looking at moss because there are actually animals and other organisms living in this moss that are very, very cool. Mm-hmm. And you might not think, you can't really see much in this right now, but if you use a microscope, you can actually see a whole world of animals just living in it, but
Okay,
it's really
perfect.
tiny.
Okay, lovely.
So this is what-
Chris, you're operating the microscope, and so you've got a sample that was taken from this in the petri dish underneath.
That's right.
Fantastic. So what are we seeing in this microscopic world?
So most of the life you can't see. It's single-celled organisms, too small even for this microscope. But we can see that there is some life.
Oh, yeah.
So you see that little writhing snake-like form there.
Yeah, that one, yeah.
So that's called a nematode. This is a group of organisms that occurs on all parts of the Earth, wherever there's even a little bit of liquid water. Bottom ocean, top of high mountains. They've been found miles beneath the Earth's surface.
So these things are in that petri dish.
From literally this exact moss as well. So,
Yes.
yeah.
There's another creature there, just creeping out of view. Let's see if I can follow her. Yeah, there's our movie star. So these are organisms called tardigrades, or if you like a more cuddly term, water bears.
Water bears, yes. Why are they interesting?
They're really, really cool creatures. So moss has this property where it dries out and then it gets wet again and it goes through these cycles. Animals like tardigrades are specialized to be dealing with that. So they can also dry out and be completely fine. And then when they're rehydrated, they go back to normal.
Can they go into more extreme conditions?
They really can, and in fact, they have been studied for that purpose. They were sent up to space. Lots of animals have been sent to space, but these were the first ones to be sent into a vacuum and come out just fine, which is...
The vacuum means that they can't breathe.
Yeah, lack of oxygen, extreme radiation, weird temperatures, all of it. So they are able to withstand very, very difficult environments, which we would not be able to.
Do we know how they survive these environments?
Yeah, so they've got some specializations in the proteins that they make, which are very specific to them. That helps protect their cells, and they have other proteins and other methods in which they can repair DNA damage, which would happen when you have a lot of radiation or a lot of cold or any of these things. They enter this thing called a tun state, where they curl up, they hide all their legs, they hide their head in their cuticle, so they're shelled. They sort of completely dry out. And once they are in an environment that's safe for them, they rehydrate, they fix up all the problems that they've had, and they carry on with their lives. In fact, when they're in this tun state, they become so light and so shriveled up that they become able to travel vast distances by air, so they can be blown away.
Yes.
And that's why we find tardigrades in lots and lots and lots of different environments. Maybe we could find them in space one day, just because they've blown up there.
Wow. So yeah, a fascinating world going on around us that we're just
Yeah.
not even aware of. Well, thank you so much, Chris and Shifty. But now what I'd like to do is introduce another type of creature. Ooh. So hello, who is this? Who am I addressing?
Samara.
Samara. And so tell me a bit more about Samara. And can I hold her?
Yes, of course.
Oh gosh.
She's a 9-year-old albino Burmese python. She's weighing in about coming under 7 stone,
7
roughly.
stone. Oh my goodness.
And just under 17 foot.
17 foot. Okay.
Yeah,
What do we
so
swear this off?
you got about 3 foot, and we got the rest of it.
Okay, lovely. Yes, fantastic. And so, wow, actually, she's lively.
She's warm.
She's warm. Yes. Oh, okay. Sorry. Okay.
There you go.
Okay. So, can you tell me more about her? And she has adaptations. She isn't trying to eat me, right?
No, absolutely not. She's just giving you a lovely cuddle.
Oh.
Can uncurl her if you want me to. But...
Oh no. I think I'm quite happy. Yes. So, tell me a bit more about her, and her adaptations.
Well, they see a lot in infrared.
Okay,
which
lovely.
there's small amounts of infrared. So like in the audience, for example, there's lots of red dots everywhere. That's what she's detecting as food or prey, of course.
Don't worry.
You know, they're detecting that, which they use with the pits on the nose, which are all the little sensors there. So eyesight is not 100%.
Oh, yes.
They more rely on the heat signatures.
Oh, lovely. So, yeah, infrared energy is heat energy, and she can detect those.
Yes.
And any other adaptations?
She's very good at holding on to you.
I know. I do like a hug.
They certainly rely on the safety of being able to hold on to something so they don't fall on the floor or fall out the tree.
Yes.
You know, they like to be relatively high up because they feel safer.
Now, it's lovely to show you sort of these different examples of life. Okay, I think I need to get myself unwound. And I think a round of applause for our animal handlers. So, We are trying to search for life out there. But one of the things is we are finding planets, but what are the chances of life actually emerging on another planet? So one of the questions we need to ask is, how did life start right on this planet? Now, to answer this question and help me find out, I'd like to invite from the Natural History Museum, cosmic mineralogist, Professor Sarah Russell. I'm sorry. I'm sorry. OK, we weren't expecting that, so please stay in your seats. We better go up here. Ooh. So I think we can go and investigate. So, Sarah, I think this is more your domain than mine. We've had a meteor strike right here in the lecture theatre. I can't see the hole where it came in from, but we'll worry about that later. So, yes, this is sort of the RI meteorite. So I think what we're going to do is going to lift it up so we can explore. But this is what you spend your time doing.
Absolutely. This is my day job. I look at meteorites, which are any natural extraterrestrial rock that falls to the Earth and survives its fall through the atmosphere. And so meteorites can come from anywhere, but most of them come from asteroids, and a few of them are from the Moon and a few are from Mars. So they can tell us about all sorts of environments beyond Earth.
Lovely. So let's go in closer.
Yes. Okay,
now, I don't know if any of yours do this.
Ooh, no.
You see, a flint-top meteorite.
Yes, they haven't had that upgrade.
Okay. So now I've got a few things inside which I'm going to show you.
Okay.
Now, first of all, I'm going to start with this. Now, the label says silicates.
Silicates.
And to me, it just looks like a bit of sand.
Yes. Well, silicates are what nearly all rocks are made of. And so silicates make up most of the Earth and also the Moon. Also, most meteorites are made of silicates.
Yes. OK, so perfect. Let's see what else I've got in here. OK, I wasn't expecting this. It says iron, but this is just an iron bar. Have you found many of these in meteorites? I'm going to put that on the table.
Right. None that look exactly like an iron bar, I have to say. But iron as well is a very common ingredient of meteorites. So on Earth, in its early history, it melted, and all of the iron and other heavy metals went down to form the Earth's core. And that melting and differentiation process also happened on many asteroids, which means that sometimes we can sample their iron-rich core. And that's exciting because we can't actually dig down and reach our own Earth's core. But we can learn about what it's made of by using meteorites.
Lovely. And I think we've got a few other things in here as well. And so I've got something here. I think that's a glycine.
OK.
And so these look like molecules.
Yes, they are.
On a bigger scale than usual. Alanine?
Alanine, yes.
Now, these are sounding familiar, but what actually are they?
Yes, so these are a very special kind of molecule called amino acids.
OK, lovely.
So, again, these have been found in meteorites. So, yeah, not all meteorites, but a very unusual type of meteorite called a carbonaceous chondrite can have a lot of organic material in it. And molecules like this, the amino acids are the building blocks of proteins. We find all sorts of organic material in meteorites that could be the building blocks of biological systems.
Lovely. So there is this theory that life started out there and it was actually seeded on Earth by things like this, meteorites.
Yes, that the ingredients for life were in space and then came to Earth where life could begin.
Lovely. OK, now this is rather on a grand scale, but I think there was a meteor strike right here in the UK not that long ago.
Not that long ago, yes. So this was in February 2021. This was in the middle of the COVID lockdown, if any of you remember that. And on a clear night in February,
so there's a fireball there.
Massive fireball was seen across the sky. And this was witnessed by over 1,000 people. So
this image, what was, so that's a camera?
Yes, so this was a camera that was actually designed to look for exactly this kind of event. We have a network of cameras across the UK looking up at the sky all the time, looking for this sort of thing. Because if we get observations from several cameras, we can work out two things. We can work out where this object came from in space. And also, if it's going to be a meteorite, we can work out where it's landed.
Lovely.
So we can go and hunt for it.
So I can understand where it's landed, but you can actually extrapolate backwards.
You can backtrack, exactly, to see what its trajectory was. So this particular meteor originated in the outer part of the asteroid belt out towards Jupiter.
Fantastic.
Yeah.
Okay, so this is a sort of a professional footage
Yes.
with dedicated cameras. But I think there was footage taken by other cameras too.
Yes, absolutely. So this was a really widely seen event, and several door cams. So these days
if we
people
look in
have
the
door
corner
cams.
there.
Oh, yep. They also caught the meteor going as well. So we have a huge amount of data.
Lovely. So you were saying you were sort of using triangulation and sort of looking at the trajectory. So where did this one land?
Yes, so we worked out that this one was going to land in the Cotswolds. So it landed in a town called Winchcombe, just outside Cheltenham.
Hence the name. Okay,
Yes,
lovely.
Meteorites are always named after the place where they
Yes.
landed.
And I was expecting some sort of impact crater. I guess,
Right.
so this is the result.
This is the result. So I don't know if you can see what we're looking at here, but the next morning, the family opened their curtains, the Wilcox family, and they saw this big splat in their driveway. And this is where the meteorite had landed.
Yes.
And they very kindly donated both the meteorite to our museum, the Natural History Museum, but also their driveway, which
A section of their driveway.
yes, it's just like a metre square section of their driveway.
Perfect. But Sarah, before I say goodbye, I just wanted to ask one question.
Yes.
Do you believe that there's life out there?
You know, Maggie, I'm pretty sure there is life out there, because I think that meteorites like Winchcombe are relatively common throughout the solar system. And if they were impacting the early Earth and bringing ingredients there, they would have also been impacting Mars and other parts of the solar system as well. And so I think it's out there.
Okay, perfect. Well, thank you very much. And a
Great.
round of applause for Sarah, please.
Thank you very much.
So we want to know if there's life out there beyond the Earth. And what we discovered over the last 30 years is that one of the best places to look is at planets orbiting the distant stars we see in the night sky. We call these exoplanets. To find out more, I'd like to introduce my colleague from the Sky at Night and planet huntress, Dr. George Dransfield. So, George, you are, I called you a sort of a planet huntress there. Is that an official title?
Yeah, absolutely. I mean, this is what I do for my day job. I search for new planets outside the solar system, orbiting any star other than the sun.
Okay, when I was at university, we thought that there might be exoplanets out there, but these stars are trillions of kilometres away.
Yeah.
So how do we go about actually trying to search for life on these exoplanets?
So, I mean, one of the key indicators that we have right now is trying to probe whether they have an atmosphere or not, and if there's signs in that atmosphere of biological activity on the surface.
Okay, lovely. So to actually explore this a bit further, I want a bit of audience participation. If you look under your seats, you will find a piece of card. And on that piece of card, there is an exoplanet on board. So what I want you to do is hold the exoplanet up, the picture of the exoplanet, and so it's facing outwards, but just have it up there on your lap. Okay, so that's, oh gosh, that's quite amazing actually. We're just getting a wide array. Now, each one of these is a true exoplanet, is that not the case?
Absolutely, this is a small subset of the over 6,000 exoplanets that we've discovered so far, and I'm seeing some lovely familiar names out there, some of my favourites in the room.
Now, you've got your exoplanet picture in the front, but on the back, I think you can see a table. Now, what is this table telling us?
So one of the things that we do when we want to select planets to investigate and do a deep dive and figure out if they could maybe host life is we look at an archive of planets that we have and we start to rule them out based on certain parameters, certain characteristics that we've measured for them. So we just try and say, okay, these ones, not a chance. We just rule them out immediately and we don't waste telescope time investigating them further.
Yes. So now you're holding up your exoplanets. What we're going to do is we're going to start eliminating exoplanets where we don't think life is likely to be. So let's start with our first parameter.
Yeah.
So here we have star type. That's the first one in your table. Yeah. So star type, what does that mean?
So one of the ways that we can classify stars is on a thing called the spectral type. So the spectral type tells you stuff like how big the star is and how hot the star is, what it's made of, stuff like that. And what I would never do is search for life on a planet around an O, a B, or an A type star.
Okay, so we've got O, B, or A. So if you have O, B, or A as your star type, please put your card down into your lap. You have been eliminated, unfortunately. We think it's unlikely that you'll find life there. Okay, so I think that's all been done. So we've lost a few, but not that many. Actually, we've still got a good, healthy population to continue the search for life.
Yeah, absolutely. And the thing is, you know, these stars, they're actually hard to form planets around anyway. They're very, very young. They're very hot. They wouldn't be a great environment.
And so next we have eccentricity. What does that mean?
So eccentricity tells us something about the shape of the orbit as the planet orbits its star.
Lovely. Okay. If your eccentricity is greater than 0.7, then please put your cards down. Okay? Okay, we're seeing some going down. Okay, we've still got quite a healthy population. So why are we eliminating these planets if their eccentricity is greater than 0.7?
So eccentricity, like I said before, it tells us something about the shape of the orbit. And so we're thinking about how squashed out, how elongated is the shape of the orbit. So the value can be from 0 to 1. If it's 0, it means it's a perfect circle. But the bigger the number, the more stretched out it'll be. And what that means is that sometimes the planet will be really close to its star and sometimes it'll be really far away. So you get huge variation in temperature, which means that it's difficult to get the stability you need for life, as we know it at least, to develop.
So let's see what we have next on our criteria. So now we have planet radius.
Yes.
Okay.
So this is quite simple. This is the size of the planet compared to Earth.
Okay, lovely. And so now we need to see the criteria. Okay, so anything greater than 2.5 times the size of Earth. So anything 2.5 times bigger than Earth, we're going to eliminate. So will you put your cards down if you're 2.5 times bigger than Earth? Okay, okay.
So when we're thinking about, again, life as we know it,
yes,
we believe that life as we know it so far, at least, it requires liquid water. So we've got to think, what are the chances of there being liquid water on the surface of this planet? And so things that are bigger than 2.5 times the size of Earth, we think they're most likely going to be gas-dominated. And so we think that this is now challenging to host life as we know it.
Okay, lovely. Okay, and so we've got one more criteria, and I must admit, I don't recognise this word. Insolation.
Yes. So insolation or insolation flux, and this tells us how much energy the planet is receiving from its host star. Again, we measure it compared to Earth. So let's have the criteria. Yeah.
Yes, so the criteria is less than 0.4 or greater than 1.5. So if you're less than 0.4 or greater than 1.5, please put your cards down. Okay, oh gosh. That was quite a decimator, wasn't it?
Yeah, that one knocked out a lot.
Okay, lovely. We still have a few left.
Yeah.
Okay, so tell me a bit more about this. So this is the amount of radiation actually reaching the Earth.
Yes, exactly. So we're looking now at the kind of the nitty-gritty. This is what's called the optimistic habitable zone. So the habitable zone is this kind of area that we define around a star that tells us whether it could be the right temperature on the surface of the planet to have liquid water. So if your planet receives between 0.4 and 1.5 times the insolation of Earth, it means that you are in the optimistic habitable zone of your star. So congratulations, you maybe have some liquid water on the surface. But I do want to give a shout out to a planet up here.
Yes.
So this is another one.
So why is this one special?
This one is very special to me. It's called TOI 715b. It's about 137 light years away. And the reason I love this one is it's because it's the first habitable zone planet that I led the discovery of.
Oh, right.
Yeah, so this one has my name on the paper for the discovery.
Yeah. So why isn't it George's planet?
Oh, I wish. But no, we actually have a convention for naming planets where it's the star name followed by a lowercase letter starting with B. Okay. But it's a lovely little thing. It's about 1.5 times the size of Earth, and like I said, 137 light years away, which in astronomical terms is really, really close. So it's a great candidate to search for life.
And thank you, George. But before you go, the question I keep on asking, do you believe there's life out there?
Oh, absolutely. I mean, one of the things that kind of guides our understanding of the universe is that the laws of physics apply the same all over the universe. So there is nothing special about this place and time, and therefore life must have happened elsewhere.
Okay, fantastic. I think a round of applause for our planet hunter.
Thank you.
In the next lecture, we're going to be exploring our own solar system, looking to see if there could be life on the planets orbiting our local star, the Sun. Now, we don't have a star to bring in here into the lecture theatre, but we have the next best thing. A traditional Royal Institution demo created using burning phosphorus, and it's known as Phosphorus Sun. Let's stand back and bask in its glow. Thank you very much. Think you've got what it takes to run a space mission? Step into command with the Open University's interactive experience and meet the experts that make it happen. Scan the QR code on the screen or visit connect.open.ac.uk/RI2025.